Good day, everyone. We are reviewing Wetzel's Limnology textbook. This is edition number 4, and we are in chapter 7, which is the fate of heat. And more specifically today, we will be focusing on the seasonal variability in mixing dynamics in response to low values of the lake numbers. The consequences of low values of the lake number vary over the stratified period. During spring or early summer, when heat has been accumulating near the surface, wind events strong enough to cause Ln to drop below 1 mixed the heat downward, often thickening the thermocline. So let's look at figure 7-25. Consequences of low values of the Verdun burn or lake numbers during the ice-free stratified period. And see chapter 8, 3b for the mechanism that enhance mixing on the basin scale. So we have your pretty much basic lake profile here. Wind with wind speed, so wind is coming from the left into the right, and we have a Verdun burn number less than 1, so therefore the lake number is also pretty low. And we have a tilting, and we have some eddies. We have some shear going on here, as well at the surface, and then we have a thermocline right here. The early summer, heat is mixed downward, thermocline thickens. Midsummer, thermocline descends. So this is the thermocline, and then this is the descending thermocline. And late summer, stratification is eroded. So there's no thermocline anymore in late summer. Thermocline before the wind, so this is the continuous line, and thermocline tilt from the wind. So this is the thermocline tilt due to the wind. Observation are similar of ice-off in Lake N2 and in Mono Lake in spring. The coefficient of eddy diffusivity in the hypolimnion of Tulik Lake exceeded 10 to the minus 4 meters squared per second, attesting to the considerable transfer of heat. During midsummer, the thermocline abruptly descends, and in late summer, it is eroded. Kz was 10 to the minus 4 meters squared per second across the thermocline and in the hypolimnion at that time, similar to predictions, and attesting to the considerable mixing. The considerable up and down welling of the thermocline in events with W or Ln less than 1 may allow direct exchange between the epilimnion and the hypolimnion on near the lake margin, similar to figure 8-21, a process known as edge leakage. Such exchanges are difficult to quantify with Kz, which inherently implies exchanges are occurring in one dimension, that is the vertical. Although the example here for the seasonal thermocline or dimictic lakes, the movement of the diurnal thermocline at low W is similar, and the associated mixing, especially if it occurs near the lake margins, where diffusive fluxes from the sediment or inflowing stream waters may have led to concentration differences between inshore and offshore waters, could lead to offshore transport of these solutes. Additionally, as will be seen for polymictic lakes, those that are assumed to mix frequently, Verdun burn and lake numbers can fall below 1. But the subsequent return of stratification as the wind relaxes implies that the wind has induced thermocline tilting and that the lakes were not well mixed. Surface energy budget, stratification and mixing in tropical lakes. Variation in solar radiation and air temperature over tropical water bodies are muted in comparison with those at higher latitude. Consequently, patterns of stratification vary with the monsoonal winds that cause movement of the intertropical convergence zone and associated cloud cover and rainfall. Thus, stratification is least during periods when the winds increase with the monsoons, and these periods are often times with decreased cloud cover, cooler air temperature, and lower relative humidity. The converse can be true during rainy seasons. That said, there is considerable variability in meteorological patterns in tropical regions. However, diel stratification and nocturnal mixing are prevalent in tropical lakes. Their relations to the surface energy budget and wind over tropical lakes is illustrated with examples from Balbina Reservoir in Brazil and Lake Yanoaca in Brazil as well. Babina Reservoir, a 170 kilometers long reservoir, is located a few degrees above the equator, and Lake Janawaka is a component of the Amazon floodplain. Data illustrated were obtained during the dry season. For both lakes, incoming shortwave radiation maxima were 1,000 watts per meter square, with fluctuation due to cloud cover. Wind speeds were low, less than 4 or 5 meters per second, but punctuated by squalls due to convective storms. While the net heat flux leading to the near-surface stratification was similar to that in the northern lakes described above, with the low winds, temperatures increased rapidly in the morning and pronounced diurnal thermoclines developed. In Babina reservoirs with KD approximating 0.5 meters to minus 1, the buoyancy frequency in the diurnal thermocline was maximally 25 cph. Whereas in Lake Janawaka, with KD approximating 1.7 m to the minus 1 meters to the minus 1, values of N in the diurnal thermocline during morning heatings were between 30 and 80 cph, depending on cloud cover and solar radiation. In both lakes, the net heat fluxes at night were minus 100 to minus 400 watts per meter square, were sufficient to erode a considerable portion of the stratification that formed in the day, such that values of N dropped below 1, though stratification was maintained at deeper depth. The patterns in Babina Reservoir are similar to those. Internal wave activity occurred in the subsurface layer, which caused the diurnal thermocline to upwell during cooling. Nocturnal mixing often reached the seasonal thermocline at night in Babina reservoir, and values of N drop below 1 above it. So this is pretty much like a description of what's going on at Lake Janawaka as well as Babina Reservoir. So I'll let you read on to that. And why don't we look at the figures here a little bit. So this is the 5 minutes averaged time series for Babina Reservoir, Brazil. And so A is the incoming shortwave radiation, SW, so shortwave radiation incoming. U is your wind speed, I believe, wind speed, and corrected to 10 meter height, with wind direction as under bars, with west, red, generally coinciding with heating, east, green, typically during cooling. So we have red, and so red is the wind is coming from the west, and then green, the wind is coming from the east. So the red means heating, and the east means cooling, and then probably the purple here is where the winds are not they're probably coming from maybe from the north or the south, not coming from the west or the east for some reason. And then the magnitude of the wind speed. So, for example, as they were saying, we have some squalls. We have some squall event, although pretty much the wind speeds were below 4 meters per second. I believe that's the unit. H is your heat flux, with total heat flux in blue and heat flux into the actively mixing layer in orange. So this is H here, and actually we have and let's see here. Okay, so we have U, we have heat loss. So let's see, heat loss of the surface energy budget, latent black, and sensible heat fluxes blue, and net long wave radiation red. So we have black, blue, and red. And I think this is what is pointing out to be. So the H here, so your heat flux here. And then the second one is your heat flux with total heat flux blue and heat flux in the active emission layer orange. So this is the second H. So this is the total H there. And and I believe the values for that are watts per meter square per second. And so we have blue, we have with total heat flux in blue and heat flux in the actively mixing layer in orange. So the total heat flux is in blue here, and then the heat flux in the actively mixing layer is right here. So where we have actually like some mixing going on when it's orange, and which corresponds to a total heat flux in this area. And then the next one is E, which is temperature contours, and F, which is your buoyancy, your N value. Okay. And so your temperature profile, so we've seen that before. We have heating events here where it's red, and we have then the depth, and these are days between 196.5 and 201 days. And so, for example, we have like the development of a thermocline in some cases, but that doesn't stay, that is not stabilized. And then we have a stable, however, seasonal thermocline right here that doesn't move that much, despite there's like a little peak here, but there's definitely like there's a change in an abrupt disturbance in the seasonal thermocline right here. Okay, and then let's look at the next one, which is Lake Janoaca, Brazil. So the surface is 40 kilometers squared, and maximum depth is 6 meters. And so we have your SW value, which is your shortwave radiation value. We have your the U, which is the wind speed. And in this case, for the wind speed, we don't have like east-west like we did here above. And then we have H, and we have so like 3 values for H. So here we have like heat loss terms of the surface energy budget. So latent is black, sensible heat flux is blue, and net long wave radiation is red. So net long wave radiation is in red, and black is your heat flux this is let's see, heat flux in so it's kind of like heat loss. So latent is black and sensible is blue. Okay, and then here we have the heat flux in the mixing layer, and then this is a total heat flux in blue. Now we have the same profile here where we have the temperature profile and then the buoyancy factor profile. And so when we have heating event, we have the buoyancy factor that increases, and we've seen that pattern before. We do have in some instances some thermocline develop, but it's pretty weak thermocline, and it's not very long lived. And that's about it for that. Why don't we look at this one now? So this is cross-section of temperature along the north to south axis of Lake Janoaca between 25 and 26 August 2016. So A is your incoming short wave and net heat loss in red. So, and then we have a value in purple as well. Incoming short wave and net heat flux in red. So we have some red. Maybe that's just the curve for the origin, although it seems to be a little purple there. Then U is your wind speed. And so in the wind direction in red, so in black we have the wind speed, and then in red we have the wind direction. And then here we have then let's see, so this is, I believe your temperature profile, right? So with morning heating and minimal winds and water stratified, although with northern wind. So this is pretty much your temperature profile along this transect. So now instead of days, we have like a north-south transect between 0 and 7 kilometers, and then we have the profile of the temperature, and I've taken at different times, like on August 25th, and then a little bit on August 26th. So for example, like in this area of the transect on August 25th at about 4:49 p.m. we have like some heating elements here, and which potentially it's like probably some tilting where it heated earlier during the day, and probably it was a wind event, like with wind moving in from left to right. It created like this tilting, and then here we have like a uniform stratified with a pretty good developed thermocline across the transect, so it's pretty uniform, pretty high temperature, and then all of a sudden it decreases pretty drastically. So we go from like probably 33 degrees centigrade to 31, and then 30, and then ultimately 28.5. So over a very short amount of distance, because this is the depth between 0 and about 8 meters. We change temperatures between 28 and 33 degrees centigrade. So it's about 5.5 degrees centigrade difference. Let's look it up here. Let's see what this one is about. So this is the time series of a Monen-Obuchov length scale divided by depth of the actively mixing layer, LMO over ZAML. So B is the temperature contour, C is the logarithm of overturning length scale with maximum value centered at the midpoint of the overturn, LT. D is the rate of dissipation of turbulent kinetic energy, and E is KZ from early morning to evening on 19 July 2013 in Balbina Reservoir, Brazil. So this is pretty like self-explanatory, although you would have to go into the detail of it to understand the usefulness of these log scales as well as the stratification. So I mean, we already have looked at that. We see that there's actually a tilting here. We have a heating event that is lasting about actually less than a day, because it's at like 200.55, and then this is 200.8. So we only have like 0.25 between the two of a day. So a quarter of a day. So over a quarter of a day, we have a developing heating event, and then consequently it changes the lake numbers and the KZ factor, and then your log E there, which is the dissipation, right? The dissipation of turbulent kinetic energy, little sigma. Okay, why don't we then move on to under ice stratification. Inverse temperature stratification is commonly found below the ice in freshwater lakes, but patterns differ from solutes when solutes are present and modify the density structure. Inverse stratification results because the temperature of maximum density of freshwaters is close to 4 degrees centigrade, and temperatures immediately below the ice are 0 degrees centigrade and increase below. Thus, the temperature profile is inversely stratified. The time required for surface temperatures to reach 0 degrees and ice to form depends on the heat content of a lake, with larger, deeper lakes having greater heat content and therefore later ice on relative to smaller lakes in the same region. Prior to ice on, lakes often continue to circulate and cool to well below the temperature of maximum density. Water temperature of between 3 and 4 degrees centigrade are common in small lakes before ice cover forms, and even colder temperatures may be found before ice on in small Arctic lake. Isothermy to less than 1 degree centigrade has been observed before the formation of ice cover, particularly in large lakes that are subject to considerable wind action. So this is Toolik Lake, and as we saw before, this is the state of Alaska, and that lake is located on the North Slope right here. Anchorage is right here, and Juneau is right here, the capital, and then these are the Aleutians, and this is the Bering Sea. So let's see, location and bathymetry of Toolik Lake, surface area of 1.5 kilometer squared, 24 meter deep, and Lake N2. So Lake N2 and E1. So we have 3 lakes. So it appears that probably they are like co-located with each other, like close to each other, rather than away from each other, from what I can understand here. Their differing bathymetry leads to differences in thermal and density structure under the ice. So Toolik Lake, as we can see, has a pretty complex topography here. So this shows the relief of the lake if there was no water. And so this is like 20 meter here. So we have like, it's like pretty deep, and then it's shallow on the east side if this is east to the right. N2 has more of a uniform pattern where it's deep on the, I guess we call it the west side here. And then it gets shallower as you move to the east. And then E1 is actually the inverse. But E1 has a pretty like deep basin there that increases in height abruptly, and then it's shallow for about half the surface area of that lake. So let's see. Isometry to less than 1 degree has been observed before the formation of ice cover, particularly in large lakes that are subject to considerable wind action. The variability in water temperature, driven by the prevailing meteorological conditions prior to ice on, thus affects the initial temperature and density stratification. The layer below the ice, where temperature changes rapidly, is called the surface boundary layer. Typically, temperature changes in deeper water are more gradual until reaching the sediment, where they may again increase. Variability in thermal structure under the ice depends on the lake morphometry, the heat budget, and sediment respiration. For 3 lakes in the Alaskan Arctic, temperatures in fall continue to decrease even after they fell below 4 degrees centigrade, the temperature of maximum density of fresh water. So we already have seen that more than once, but we know that 4 degrees is actually the temperature maximum density of water. I'm not sure we need to repeat that, but anyway. And then temperatures appear to be isothermal, although examination of high resolution data indicated that up and downwelling from internal wave motions persisted even as temperatures decreased. When water temperatures are less than 4 degrees centigrade, incoming solar radiation in warming the surface waters increases density near the surface, which can induce convective mixing, penetrative convection, whereas heat loss can contribute to stratification. Solar heating of shallow regions can create denser water, which can flow offshore as gravity currents at deeper depths, stabilizing the water column. These processes lead to variations in thermal structure prior to and after ice on. So, figure 7-31. So what do we have here? So we have thermal structure and time series of changes in specific conductance during winter, leftmost panel, fall, middle panel, and shortly before and after ice off, right panels. In the 3 lakes beginning in the fall of 2010. And DOY 250 is 7 September and ending in spring 2011. Ice on fall can be identified by temperatures becoming inversely stratified. Ice off can be identified in spring as the time when temperatures rapidly increase in the upper water column because of the increased density from increased solute in lower column of all 3 lakes and additional density gradients as snow melt freshened near surface waters, mixing from penetrative convection prior to and at ice off either did not occur or did not penetrate through the full water column. So this is your the set of lakes here. So we have Toolik Lake here for this set of graphs. We have N2 for this set of graphs, and then E1. So on the leftmost here we have your stratification, your isotherms with depth, so depth here, and then the number of days here. So we have between 250 and 500. So 250, as I was saying, is 7 September. So this is 7 September, and all the way then therefore to 250 days from 7 September, which probably is maybe sometime in May of the next year. And so do they say that actually? And ending in spring, 2011, okay, 19 June, and this 535, 19 June 2011, okay. So 535 is right here. So we have like 7 September to the spring, and late spring, really, because 19 June is very close to the summer solstice. And let's see. So here it looks like, I'm not sure why we don't have data here, but let's start right here. And so what we see is they were talking about inverse stratification in the fall as ice is forming over the lake. And so that would mean that we have warmer temperatures at the bottom than we do at the top. And that is actually the case really throughout the life of that lake from September through June. This is your temperature data as well, and then here as well. So we have a specific conductance at the different depth and microsiemens per centimeter, and so that is an indicative of as the conductance increases, that would mean that you have some amount of stratification, where if it decreases, you have a pretty good mixing. And so here in the summer, we have pretty good mixing, and because the lake is not yet fully stratified, or it's probably going like an early September before ice on, it's probably like the thermocline is not probably very strong. And then this one, so the panels here, and middle panels, so shortly during winter, leftmost panel fall, middle panel, and shortly before and after ice off, right panels. Before and after ice off, right panel. So this is according to, this is the winter time / the fall. And then the middle panel is, let's see here again, it's the fall. And then the shortly before and after ice off, and in the 3 panel, okay, and then in the spring. So leftmost panel, the winter, fall, the middle, and shortly before and after ice off, before and after ice off on the right side. So before ice off, and then the period where we have breakup right here, and there's no more ice. So here we have like presence of ice, and we have this inverse stratification going on. We have warmer temperature at the bottom than we do at the top, and then the ice is gone, and then we have a heating event that is affecting the surface water. So we have the same pattern here. This is the fall, and so in the fall you have pretty good stratification here. I mean, yeah, stratification as well as thermocline, and then we have erosion of that thermocline with the start of the presence of ice, because we have an inverse stratification right here. We have warmer temperature at the bottom than we have at the top. Okay, despite weak stratification prior to ice on, the water column can quickly stratify under the ice. Several co-occurring processes contribute. Heat fluxes from the sediments warm the overlying water and create downslope flows such that warm water accumulates in the deepest location. Sediment respiration and potentially intrusions of warmer groundwater may lead to an increase in solute, which also increase near bottom density and contribute to the flow of gravity currents downslope. At temperatures under the ice in freshwater lakes, solutes contribute to density even in lakes as fresh as Toolik Lake, where specific conductance in summer is low. Calculated velocity of the gravity currents are on the order of a few millimeters per second, thus flow to the bottom of a small lake, assuming distances of 50 to 200 meters, would only take a few hours. Additionally, if the water column mixes immediately prior to ice on, the temperature of the mixed water may vary across the basin, being warmer over the deeper region. The cooler, less dense water will flow over the warmer water on relaxation of the wind, leading to an overall increase in stratification. In both Toolik Lake and nearby Lake N2 in Alaska, near bottom heating is apparent in the days following ice on. The flow, so we have like, they're telling us like that at the onset of ice on, which is right here, for Toolik Lake and N2, we have heating coming in from the sediment. So we have like the sediment have stored some amount of heat and is releasing that heat when there is ice formation at the surface of the lake. And this is not as much the case for E1. So let's see. The cooler, less dense water will flow. Okay, so thus flows of the bottom of the small lake, assuming distance of 50 to 200 meters, would only take a few hours. Additionally, if the water column mixes immediately prior to ice on, the temperature of the mixed water may vary across the basin. The cooler, less dense water will flow over the warmer water on relaxation of the wind, leading to an overall increase in stratification. In both Toolik Lake and nearby Lake Into in Alaska, near bottom heating is apparent. Okay. So thickness of the surface boundary layer with its colder water increases over time. Ultimately, in shallower N2 temperatures begin to decline throughout the water column due to heat flux to the ice. In contrast, in deeper Toolik Lake, temperatures continue to increase to at least the mid-region of the water column. Increases in specific conductance indicative of sediment respiration continue over winter, with the largest increases near the bottom. In small lakes in warmer regions where surrounding soils have not frozen, groundwater intrusion may contribute to the flow from gravity currents. The combined influence of increased specific conductance and increased temperature near the bottom leads to an appreciable increase in near bottom density. Consequently, as winter progresses, gravity currents from continued heat loss from the sediments or sediment respiration would flow over the denser bottom waters at progressively shallower depth. Other processes may also contribute to flow under the ice. For example, temperature fluctuation occur in the middle of the water column in Toolik Lake. These are coherent with changes in wind velocity, implying the signature of internal waves. These motions have been shown to induce slow oscillatory flow in other ice-covered lakes. So occur in the middle of the water column in Toolik Lake. So like we have temperature fluctuation occur in the middle of the water column in Toolik Lake. So figure 7-31. So they're telling us here that in Toolik Lake, in the middle column, we have like fluctuation in the temperature, and I mean right here, for example. But we've seen that at other lakes, and it's not necessarily like indicative of an Arctic lake behavior. And that would be actually under the ice. So like they're telling us like under the ice, when there is ice, that we have like fluctuation in the temperature values. And so here we have to assume that probably in the winter here we have some fluctuation right here in the middle water column. Okay, so let's see. Malm's analysis implies that they do not cause mixing in the interior of a lake. The extent to which they induce mixing near the boundaries is not known. Cryoconcentration, the exclusion of solutes when ice forms, may lead to solute concentration immediately below the ice that are higher than those below. With temperatures increasing below the ice, these combined conditions can lead to convective motions known as double diffusion. Modeling indicates that instabilities can develop under the ice that ultimately modify stratification. The thermostructure of Lake E1 differs from that of the other two lakes discussed above in that the layer of warmest water is in the mid-water column. The layering of warmer water has been observed in this lake for all the years for which the data are available. The warmer water is attributed to offshore flow of water from the shallow western basin of the lake, which had been warmed by heat fluxes from the sediment, rather than sink to the bottom. The water intrudes offshore at depth in the main basin where the density is similar. So they are telling us for Lake E1, they are telling us that the warmest temperature are in the middle water column, and it's like right here, like we have pretty warm temperature and then cooler here, and it's not as prevalent when we have like in the fall here, when we have no stratification, like we have ice on, of course. But at the same time, we don't have much also contribution of an inverse thermocline that we've been used to with ice on for the other lakes. So, and then here we also have a heating event at the surface with let's see. Calculation of complete heat budgets under the ice are rare. One of the earliest detailed studies on winter heating showed that most, greater than 75% of the temperature increase is from solar radiation. This large fraction may result from the temperate latitude of the lake studied, and is only possible if there is little snow on the ice. The contribution from the sediment was computed based on the profiling of temperatures into the sediment over an annual cycle. The relative contribution of heat stored in the sediment during the summer, which enables heat flux to the overlying water under the ice, will vary from lake to lake in relation to the morphometry, summer heating conditions, and other factors. Measurements of sediment heat flux indicate that they are of the order of 5 watts per meter squared, with higher values in shallower sediments. Heat budgets for Toolik Lake indicates solar heating warms the water only for a few weeks after ice cover, with maximum value of 15 watts per meter squared when the ice is snow-free. Mortimer and McCurth analysis indicate that heat flux from the sediment and production of solute by sediment respiration would produce gravity currents that transport the heat and slightly more solute-rich water to the deeper parts of the lake. The increased density induced by the downward flow of solutes released by sediment respiration enables near bottom temperatures above 4 degrees C, as been observed in some shallow lakes. A transition in the mixing dynamics of ice-covered lakes can occur in spring when temperatures are below 4 degrees C. Solar radiation penetrating through the ice can create instabilities as it warms water closer to the surface to temperature exceeding those in the water below. This process is known as radiatively driven convection or penetrative convection. The turbulent eddies that form are initially small as the instabilities begin but progressively deepen. In Toolik Lake, they can reach the bottom 24 meters in years with minimal chemical stratification from solute. These eddies help maintain negatively buoyant phytoplankton, for example diatom, in suspension, enabling blooms under the ice. When water heats more rapidly inshore than offshore, nearshore water may flow offshore, penetrating at depth with similar density. This process, horizontal convection, is another form of RDC. It can lead to offshore transport of water with higher concentration of oxygen or phytoplankton, which have been going near shore. Density stratification on the ice is often accentuated near the bottom by dissolved solutes and at times in a layer below the ice due to fresher water from snowmelt or ice melt. In such cases, mixing under the ice by RDC may not occur and full mixing is delayed until after ice off. Different scenarios for the success of phytoplankton under the ice with or without RDC are presented in Jensen. The convective mixing beginning under the ice and in some cases continuing or beginning afterwards can be highly energetic, and in large lakes the convection cells may reach 185 meters and be 50 meters wide. The thermal bar seen in large lake is described in chapter 8 for warming processes in deep lakes with larger inflows. The extent to which incoming snowmelt or river water is mixed under the ice also depends on whether there is sufficient solar radiation to induce penetrative convection and whether density gradients restrict the ensuing mixing. For example, in figure 7-4, water whose temperature exceeded 6 degrees C was centered around 1 meter in late March in Lawrence Lake. The ice at this time was weak and porous from warm rains. Water low in dissolved solute which had entered through the ice or possibly from the margin of the lake was less dense than that of the water below due to the higher concentration of dissolved ions in the lake water. By this means, solar heating through the ice increased the temperatures in this dilute layer without producing instability. Temperature anomalies such as this one may be transitory and are likely related in part to air temperatures rising above freezing and advective inflows of warm water from the periphery of the lake. Cortez et al. Illustrate the initially cold snowmelt intrusion that flowed directly under the ice. Over time, as stream temperatures rose above 4 degrees C, temperatures in the inflows were warmer than the lake water, but inflows remained near the surface due to their lower solute concentration and correspondingly lower densities. The freshwater lower specific conductivity in these inflows relative to lake water precluded or reduced the depth of penetrative convection. Pash et al. Illustrate the persistence of carbon dioxide enriched river inflow under the ice at a depth of 10 meters in a year when penetrative convection extended to 10 meters and the velocity of the thermals was low. The plume persisted when there was some snow cover on the ice and the magnitude of the diffuse attenuation coefficient, KD, in the water was 32 meters to -1. In a year when convective mixing reached 24 meters, snow covers on the ice was minimal and KD was 1.2 per meter. The incoming river plumes are expected to be dispersed through the water column in such years. The extent of such mixing can then affect the distribution of incoming nutrients and the rate at which climate forcing trace gases such as CO2 are emitted into the atmosphere. A detailed resume of the types and characteristics of the lake ice is given in Hutchinson 1957, two books by blah blah blah, by Ficke and Ficke summarize the diverse literature on the properties of ice and the thermal characteristic of lakes and rivers under different conditions. More recent works and model studies, thermodynamic consideration have often been separate three layers with different attenuation coefficients. For example, blue or black ice, which is clear ice, white ice, which is ice with snow interleaved, and snow-covered ice, with these distinctions important for calculating the heating of the water below the ice. So that will be completing our review of this section of Chapter 7 of Wetzel's Limnology textbook, and I'll see you tomorrow, and thank you for sticking on with me today and to go over this pretty intense and information-rich content. And I'll talk to you soon. Thanks. Bye.